quickly, I wanted to touch on number 1 because I made an error in this one. It was the last question from yesterday's session. So I just wanted to go over this again. I don't think a lot of people were here for this because this was past when the session technically ended. So not a lot of people saw this, but I just want to touch on this just to be safe. So I'll just give you guys like a minute. Okay, so that was about a minute. This one probably shouldn't take more than that anyway. So go ahead and spam your answers in the chat box. Good. Yep. Good. So yeah, the answer is B, right? So I messed up and I said the answer was A in the last session just because I had an aneurysm. I don't know. It's because it's easy to just mess up because neon is right over there in the periodic table, and the trend technically says that it increases up to that corner, but noble gases are actually less electronegative than those halogens are going to be. So those halogens are very electronegative, and not only that, fluorine is going to be the most electronegative element on the periodic table. So just wanted to touch on that really quick. Okay, so let's see. No, does anyone have any questions over this one? Okay, so all right, so now we're shifting into chapters 11 and 12. So as far as these molecular orbital problems go, I flat out skipped that section in that last SI session just because they're so low yield, and I wanted to touch on intermolecular forces more because those are very important. So with these, in my meeting with Hope Weeks, she said that for all of these problems, they're going to give you the actual diagram. So in terms of this blank diagram here, you don't need to worry about making it because it would be so much harder if you had to actually know how to make that template. So they're always going to give you the blank template, which makes it a lot easier. And there will only probably be one question, if any, on the final exam that has to do with molecular orbital theory. Okay, so if you're super worried about this stuff, it's not a huge deal. It'll only be maybe a question. So go ahead and do this one. I'll give you guys 3 minutes to work on it, and we'll go through the answer. It is, honestly, it's easier than it looks. It looks super hard, but once I go through the answer, you'll see how it's really just not that bad. At least compared to, other problems in the course, I guess. Yeah, only one question. That's facts. Okay, so go ahead and spam your answer to this in the chat box. Good. Yep, the answer is A. Okay, so let me address some chat box questions first. Okay, there was one thing up here. Oh yeah, okay, here it is. So someone asked, I think I missed this. So someone asked, are noble gases like the least electronegative on the periodic table? Probably not the least, because the trend says that it increases moving from left to right on the periodic table. So those group 1 and 2 elements are going to be the least electronegative. Okay. Let's see. So someone said, is this like putting arrows into boxes? That's basically all you do. Yeah. Yeah. So if you're overwhelmed by this, first, just to warm you guys up, think back to the SI session about electron configurations. If you went to that, where basically what I did is I had you guys fill in the electron diagrams, the valence orbital diagrams with all of the electrons. Starting at hydrogen, we moved up maybe 10 elements, and you just saw how you added 1 electron each time each atom you went, or each element. This is basically very similar. So this is an orbital diagram where these orbitals right here, those are your atomic valence orbitals. You don't fill those in when you're filling in these diagrams. So those, honestly, if you're not taking chemistry past organic chemistry, these are just irrelevant to you, okay? So, thinking about this, on a super high level is really not important if you're not going to be taking any later on classes. And honestly, in those later on classes, that's when you actually understand these diagrams. In Gen Chem, it's really just a matter of, solving the problem, okay? And just learning how to solve the problem, that's easy. So ignore these. So we don't worry about these when we're doing these problems. It's these orbitals right here. These represent the molecular bonding orbitals, okay? And it actually has a label right here. So atomic orbitals and molecular orbitals. That has to do with the bonds, and that's what we're sort of, looking at, right? Because we're looking at molecules like F2 2 plus, O2 2 minus, O2 2 plus, and Ne2 2 plus, okay? So they're just diatomics, right? So they're diatomic atoms, 2 atoms bonded together. So the way you want to attack this, you want to do this in 3 steps, okay? So first step is to find the total number of electrons like you would in a Lewis structure. So total number of valence electrons.
God damn.
Yeah, it's right now.
Yeah, it's 7:41.
Someone's not muted.
All right.
It's okay.
Almost done.
That's awkward. Okay. So yeah, the first step is to find the number of valence electrons. And then the second step is you basically fill in the diagram. So fill in the diagram like you would with those electron diagrams for just valence electrons, okay? And then the third step for this problem, it's asking which of the following is paramagnetic. So that's just remembering the definition where paramagnetic has unpaired electrons. Okay, so what's going to happen is we're going to fill in electrons for each of these molecules, and one of them is going to have a diagram where there's unpaired electrons, and that's the one that's going to be paramagnetic. Okay, so the answer choice is A, but because the answer is A, I'm going to start at B just to work our way up to why A is the answer. Okay, so starting with B, oxygen is going to have 6 valence electrons, and there's 2 oxygens in O2 2 minus, okay? So that comes out to 12 total valence electrons, but this is 2 minus, so we're going to add 2 electrons to this. Be very careful here because
Will we do it again? The wealth of natural resources?
Okay. So be careful here because 2 minus means 2 additional electrons, 2 additional negative charges. Okay. So it doesn't mean 2 less electrons. It means 2 more electrons. Okay. So that gets us to a total of 14 valence electrons for O2 2 minus. So now it's just a matter of filling these in, doubling them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So in this diagram here, you just work your way up as the levels increase. And in this case, all of these electrons are going to be paired. So O2 is going to be diamagnetic. O2 2 minus is diamagnetic. Okay, so that's not an answer. Next up, we'll do O2 2 plus. So oxygen, 6 valence electrons. There's 2 of them, so that's 12. But this is going to be a 2 plus charge, so we're removing 2 electrons this time, so that gets us to 10. Okay, so filling this one in, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so again, they're all paired, so it's diamagnetic. Okay, so that's not an answer. Next, let's do neon. So Ne2 2 plus. So neon is going to have 8 valence electrons, and there's 2 of them. So that's 16 valence electrons, but this is a 2 plus charge. So we're removing 2 electrons. So this has a total of 14 valence electrons. So filling this in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, those are all paired, so it's diamagnetic. Okay, so now let's get to F2 2 plus. So with F2, so fluorine is going to have 7 valence electrons. There's 2 of them, so that comes out to 14, but there's a +2 charge, so we're removing 2 electrons and we get 12, okay? So we got to fill in 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so remember when we're dealing with subshells right here, where there's multiple boxes in that one level, first we go and try and give them each their own box, and then if we have to double up, we double up, but only if we have to. Okay, so we don't have to double up, so we're not going to double up, and in this case, those 2 electrons there are unpaired. So that makes F2 2 plus paramagnetic. Okay, so it really is just that simple. So you don't need to worry about drawing the diagram. You just fill in electrons and, figure out which is paired and which isn't. Okay, let's check the chat. Okay, so someone asked, does the final usually cover everything pretty evenly? It should. I asked Hope Weeks that, and she said it's generally even. There won't be a disproportionate amount of chapter 11 and 12 material, because you might think, oh, we haven't had a test over that, so it's going to be a lot of chapter 11 and 12, but it's going to be pretty even. And there's going to be plenty of gimme questions in there too. If you look at the practice exams, some of those are just really easy. Someone said, so you start at the bottom? That's correct. You just start at the bottom and work your way up. So someone asked, will we get any questions about bond orders? That's possible, and I'm pretty sure there is a question at the very end of this session about bond orders. Okay, yeah, so we'll talk about bond orders when we get there, but it's really just a formula. There's nothing more than that. Yeah, we're going to talk about pi and sigma bonds later on. So someone said, so what does this actually tell us? That's a good question. That's like way beyond the scope of the class. That's why I said, like, for these molecular orbital problems, you just learn how to solve them. They don't really go teach you why they're important very well. Okay, someone asked me if there's going to be a Clausius-Clapeyron equation on the final. No, that don't need to worry about that. Yeah, I agree. It is frustrating. I was not a fan of these when I took the class. Okay. Yeah, so an atom is paramagnetic if it has any unpaired electrons. So even if there is one unpaired electron, it's paramagnetic. So diamagnetic, all electrons have to be paired. Okay, good question. All right, so that was number 2. That and one other question should be the only molecular orbital questions on this session. So it's basically just a matter of knowing how to fill it in, and if needed, knowing how to do the bond order, and we'll get to that later on. Okay, so that was the first page. So let's go ahead and move into number 3. So I'll give you guys 2 minutes to go through that one. Oh, also another thing I want to say is that those molecular orbital problems, they're only going to talk about diamagnetic molecules. Okay, nothing more complicated than that. So only 2 things bonded together. So apparently I just realized I'm competing with the Carol of Lights right now. So that could have been why there weren't a lot of people in Michaelin's session. At least I think I am. I'm pretty sure it's tonight. Okay, so it's 53. So let's go ahead and go through this one. So I'm seeing more people than usual on my problems saying they're stuck. So Yeah, it really does take over your life. Okay, so that could be because we really kind of just had to cram 11 and 12 into one SI session like a week ago, I think. Like it was the session before Thanksgiving break, I believe, something along those lines. But so yeah, that could be why they just like to cram that stuff in at the end of the semester. So with intermolecular forces, you have to know, there are three that I would know, okay? There's three more, but there's really only three important ones. So one is London dispersion forces. Another one is dipole-dipole. And a third one is hydrogen bonding. Okay, so if you don't know what those are, you don't know them well, then definitely research those after this session, because a lot of these chapter 11 and 12 problems are going to ask about intermolecular forces on the final. Okay, so since we're talking about hydrogen bonding, what you need to know is that for hydrogen bonding to happen, first, hydrogen has to be on the molecule and it has to be attached. Oh, I think someone's unmuted. All right. I'm pretty sure I turned on mute upon entry, but maybe I forgot. Okay. So for hydrogen bonding to happen, hydrogen has to be attached to the molecule, but not only does it have to be attached to the molecule, it has to be attached to a phone. So a phone is fluorine, oxygen, or nitrogen. Okay. So in any molecule where hydrogen is attached to fluorine, hydrogen is attached to oxygen, or hydrogen is attached to nitrogen, then you know that hydrogen bonding can happen, okay? So this could be attached to other parts of a molecule, okay? So R just refers to, could be some big molecule or, basically you just have an H bonded to a phone, okay? So that's when hydrogen bonding can happen. So what we need to do is we need to look at all of these molecules in each of these answer choices, and we need to look for one, the hydrogen, and two, it bonded to a phone. So just remember the acronym phone, fluorine, oxygen, nitrogen, and you won't mess up. Okay, so first of all, the answer is C. I forgot to have you guys spam, I think. So the answer is C. So hopefully you got C. But anyway, looking at A, we have a fluorine right here. So that fluorine is just attached off. But you might think, oh, it's attached to a hydrogen. That's not so. So this molecule actually looks like this. So for me, this is easy because all of these, like I can just picture these in my head taking organic chem, but chances are you're going to need to draw these out, okay? And so when you draw it out, you get a molecule that looks like this. And so now you can see that fluorine is attached to the carbon, that hydrogen is attached to the carbon. So that hydrogen itself is not attached to the phone, okay? So that's not valid. Hydrogen bonding is not happening there, okay? So next, let's look at answer choice B. So that's CH3, 3 nitrogen. So that one is going to look kind of like this. CH3, 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 and nitrogen. Okay, so these are so much easier to do in the skeletal form that we learn in OChem, but generally that's a carbon, oops. So that's a carbon, that's a carbon. Think of it as attached to hydrogens like so. So what you can see here is that nitrogen is attached to the carbon and those hydrogens are not attached to that nitrogen. Okay, so all those hydrogens are just attached to the carbon. So hydrogen bonding is not happening there. Okay. But if we look at C, this says CH3, CH2OH, and it's making it pretty clear that that hydrogen is bonded to the oxygen. But just in case you don't believe me, let me just draw it out. So we have our CH3, our CH2, and our OH. So we can see that that hydrogen is bonded to that oxygen. It's a phone, so hydrogen bonding can happen there. Okay, next up, D, hydrogen is bonded to iodine. That's not a phone, so can't happen there. E, those hydrogens are not attached to that oxygen. So to draw this out, that looks like this. That's an ether. If you breathe in too much of this, you'll pass out. So that oxygen is attached to the carbon there, and the hydrogens are not attached to the oxygen. So hydrogen bonding cannot happen in E. Okay. So the key takeaway from this is it has to have hydrogen bonded to a phone, and most of you guys are going to need to draw these out before answering because it's easy to slip up here. Okay. All right. I'm just checking the chat box. Yeah, we do need a raise. Yeah, so someone said, so if it's got a subscript, it's not attached to the element after it, just the one before it. That's true. Yeah, you can think of it like that. Okay. Yeah, I had to scroll through a lot of that to see if there were any questions. Okay, so just want to double check. Does anyone have any problems with 3? There's more problems with hydrogen bonding in this session. So if you're worried, then there's more problems here. So don't fret. Okay, so I don't see any questions. So let's go ahead and move to 4. So I'm going to go ahead and erase some of this stuff. So I'll give you guys 2 minutes to do 4. That should be more than enough. So at 03. Okay, yeah, most of you guys are done. So I'll do it at 02 because it's quickie. All right, go ahead and spam your answer. Good. Yep, the answer is B. Okay, so just know that in a single bond, you have 1 sigma bond and no pi bonds. Okay, and in a double bond, you have 1 sigma bond and 1 pi bond. And in a triple bond, you have 1 sigma bond and 2 pi bonds. Okay, so that's just something you need to know. All right, so if we look at this molecule, it's asking for how many pi bonds there are. Okay, so first we know, according to this, pi bonds are only going to occur in double and triple bonds. So we have a double bond over here and a triple bond over here. So we know that in a double bond, we are going to get 1 pi bond. and in a triple bond, we're going to get 2 pi bonds. So there's a total of 3 pi bonds in this whole molecule. Maybe a question or two. Yeah. Honestly, since it's the final and it's cumulative, I'll just say for each content area or each type of problem, a question or two. Really, it just depends what they feel like. Some areas just won't get tested on and some will, but I highly doubt, a certain area will get tested on a lot compared to the others, except for like stoichiometry. There's probably going to be a lot of stoichiometry. Okay. So does anyone have any last questions over 4? All right. So let's go ahead and move to 5. So I'll give you guys 2 minutes to do this one. Just get them correct. You got 50 questions? No biggie. I saw that, like, the TikTok physics professor, he was like, my students always complain about getting low scores. Just get them correct, LOL. Oh my gosh. All right, so it's 8:06, so let's go ahead and go through this one. All right, so this says, which of the following pure substances has the highest boiling point? So we talked about the multiple types of intermolecular forces right here. So London dispersion, dipole-dipole, hydrogen bonding. Obviously, these are all going to be treated as individual atoms sort of in a mixture, right? So no dipole-dipole because you can't have a dipole in a single atom. Obviously, no hydrogen bonding either. So the only type of intermolecular forces we're going to have are London dispersion forces. And so with those, the thing that matters is the mass, okay? So when you have a higher mass, then you will have higher London dispersion forces, okay? So the idea behind London dispersion forces is that in any molecule, think about your molecular orbitals. Those are areas where you have a high probability of finding electrons. And in real life, those electrons are moving around. So if you think about a molecule, those molecules are all moving around the electron. And there's a very, very, very slight chance that at some given moment, those electrons could all happen to be perfectly aligned to where they form a very temporary, brief dipole. And so that dipole can cause attractions between molecules. So that's the idea behind London dispersion forces. So because of that, the higher mass a molecule is, the more orbitals there's going to be, there's more opportunity for those electrons to move around, which means the chances of those electrons forming some kind of a dipole increases. So that's why when you have higher mass, you're going to get higher London dispersion forces, okay? And so that's the exact logic you need behind number 5. So also, I think I forgot to have you guys spam. So go ahead and spam your answer first before I reveal it. Yeah, good. So it's E. Yep. So xenon is basically just the highest mass of each of these choices. So that's exactly what you want to look for. So nothing about charges. I think I saw people mention charges. It's really just size. Okay. So with London dispersion forces, it's only the size. Some people talk about like the symmetry of the molecule and the surface area of the molecule. That's how I learned it originally, but then I came here and I don't think the department teaches that. They didn't even mention it in OChem, so just only think about the mass in terms of London dispersion forces. So someone's asking, so from the top to bottom, it increases. What about side to side? So it's only the mass. So you just look at the atomic mass as it's printed on the periodic table, and that's which one has the highest London dispersion force. Okay, so it's not really a trend. It's just looking at the table to see which one has the highest mass. And when we're talking about molecules as a whole, right, because these are just individual atoms, then you'll just sum up the molar mass of the whole molecule. Okay. So the higher the mass, the higher the boiling point. Yes, because the stronger the IMF is, the more energy that you have to put in to cause it to vaporize. So, yeah, higher mass, higher boiling point. Okay. So are there any more questions over this one? All right. So now let's go ahead and do number 6. So I'll give you guys 2 minutes for this one. Oh, yeah. They love talking about surface tension in AP Bio. There was an FRQ question over it when I took it. It was a math question, and it was like, it gave us 2 cells, and it gave us the surface area of both cells, and it just had us like write down the number of the cell that had like the most efficiency or something. And so like one was 18 micrometers squared and one was 9 micrometers squared. And so I just put the highest one because that's the most efficient. My AP Bio year, when we took it, our FRQ section was just utterly disgusting. Like they straight up essentially asked us to cure cancer. Like I'm not even exaggerating that in the slightest. It was so terrible. I didn't learn anything in my AP Bio class because it was too easy. Maybe if Miles is in here, he can vouch for that. Because like at other class or other schools, it's super hard, but like, I don't know, it was easier at my school, I guess. We just watched the Bozeman videos and took the exams. Oh yeah, I took BC Calc. I'm glad I did because now I don't have to take Cal 2. For BC Calc, we actually had to cram all of the actual BC content into the very last 2 weeks of the class because our teacher had a car accident. So like he was out for a while. So I basically I was a senior, so I didn't pay attention. So I basically just watched, I randomly selected 2 Khan Academy videos. I was like, okay, here's 2 8-minute long videos. I watched those the night before the exam. I was like, all right, that's just what I'm gonna do. And so I ended up doing really well because I did well on all of the AB questions because the AB part was really easy. So yeah, I got a 5 on that one. All right, so let's go ahead and go through 6. So 6 says, which of the following pure substances has the strongest dispersion forces? Okay, so dispersion forces, that gives it, really easily to you. We're talking about London dispersion forces again, so the same concepts apply. All right, so we're just looking for which one has the highest molar mass. So go ahead and spam your answer for that in the chat box. Perfect. Yep. So B, just because carbon has such a higher molar mass compared to hydrogen, I don't even care about the hydrogens really. I'm just going to count the carbons, and B has the highest amount of carbons, so I'm just going to say that that's the highest molar mass because I don't want to do extra work. So yeah, basically B has the highest molar mass, so it has the highest London dispersion forces. It's just the exact same logic as number 5. Okay. So does anyone have a problem with 6? All right. So let's go ahead and move on to 7. So I'll give you guys 2 minutes to do that one. Oh yeah, for sure. They will. Yeah. They could just give you entirely, unrelated molecules, and you'll just have to count up the molar masses individually. All right, go ahead and spam your answer to number 7. Good. Yep, so the answer is B. So this one is just a matter of drawing the Lewis structure and figuring out the hybridization. So this is HCN, so we have a hydrogen, we have a carbon, and we have a nitrogen. Okay, so counting up our valence electrons, we have 1 hydrogen that's got 1 valence electron. We've got 1 carbon, which has 4 valence electrons, and we've got 1 nitrogen that has 5 valence electrons. So this gives us a total of 10 valence electrons. So we fill those in 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we know nitrogen likes to form 3 bonds, so we'll give that triple bond over to nitrogen. Hydrogen only wants those 2 electrons. So this is our structure for HCN. So now we need to figure out the hybridization on that central carbon atom. And there's only 2 things bonded to it, so it's going to have just sp hybridization. So that's our lowest form of hybridization that we can get. Okay, so yeah, so that's 7. So someone's saying all the electrons are bonded. I don't know what you mean. Are you saying all the electrons should be in bonds and not as lone pairs? because nitrogen should have that too, lone. Oh, yes. Yeah. So, yeah, that brings up a good point. The number of lone pairs doesn't matter for hybridization. It's just the number of things bonded, right? So there's only two things bonded to that carbon. So it's just the hydrogen and the nitrogen, and that causes it to be sp hybridized. So remember, two things bonded to the central atom is sp, three things bonded to the central atom is sp2, four things bonded to the central atom is sp3, five things is going to be sp3d, and six things is going to be sp3d2. Okay, so you can't get lower than one because then you only have two atoms bonded together, right? So so someone said they thought it was the number of groups total. That's correct. What I'm saying is that just count the total number of groups. Don't omit the lone pairs, because some people omit the lone pairs when they count the things attached to the central atom. So like some people could do NF3, for example. So this is NF3. Some people may say this is only sp2 hybridized because they don't count that lone pair because they differentiate it between the others. I'm saying it doesn't matter. It's four things bonded to the central atom, so it's sp3 hybridized, right? So the lone pairs count as a group, an electron group. I think maybe I wasn't clear when I said that earlier. Okay. Someone's saying, couldn't you look at the periodic table? Interesting. I've never heard of looking at the periodic table to determine hybridization. Yeah. Okay, so yeah, just to double down on this one more time, you count the number of groups bonded to the central atom. So lone pairs plus atoms, okay? All right, so does anyone have any problems with 7 before I move on? Okay, so let's go ahead and move on to 8. So I'll give you guys another 2 minutes for this one. I'm giving their session. Okay, so go ahead and spam your answer to number 8. Yeah, so good. It is A. Yep. All right. So let's go ahead and go through this one. So we need to draw our structure for CO3 minus. So this one is going to look like this. Okay, so we have 3 oxygens and we have 1 carbon, and so our structure ends up looking like this. So we sum up our valence electrons and we arrange them like so. And so just to touch on this just a tad more, this one is going to end up having multiple resonance structures, but that's not really important. I just wanted to highlight that because it popped into my mind. But anyway, this is our Lewis structure for CO3 minus, okay? So now there's no lone pairs, so we're just counting the number of things attached. So there's 1, 2, 3 things attached. So this makes it sp2 hybridized. So that carbon is sp2. Okay. All right. So does anyone have any questions over 8? Yeah, so you'd add an electron. Yeah. So let's go through. Oh, perhaps I mistyped. Yeah. It should be CO3 2 minus. Okay. Yeah, so I did something wrong with the question, so that means my key is probably wrong. So what I'm going to say is let's go through number 9. So do number 9, and then I'll figure out what I did wrong for 8. So go ahead and do that one. Okay, yeah, so I did end up mistyping, so this should be a 2 minus. But it does stay as sp2. Okay, so this is our Lewis structure for CO3 2 minus. All right, so let's check the chat. Yeah. So yeah, if you answered A, it's correct. So for 8. Oh my gosh. She's a friend. Okay. So, all right. So that's basically 8. It's just I mistyped. So it should be CO3 2 minus. So that was just a problem with my key. So this structure is the structure for CO3 2 minus. Okay. So now let's go ahead and do 9. So go ahead and spam your answers for 9. I mean, she knows if she calls me this time and I like hang up like that, then I'm in an SI session. Like she's texted me multiple times when I hang up, like, oh, you're in an SI session, sorry. I mean, good friends do call often, that's true. Okay, so someone said, so if they asked what oxygen's hybrid orbitals will be, would it be the same as carbon? That's a good question, actually. So just to repeat the question, someone asked, so if they asked what oxygen's hybrid orbitals will be, would it be the same as carbon? The answer to that is no, okay? So just going back to 8 really quick, hybridization only happens in the central atom, okay? So what's happening is you have this carbon here, and it's going to stick off these little sp2 orbitals, okay? So it's going to look something like this. I'm just a terrible drawer right now. Okay, so those are our sp2 orbitals. And what happens is those are going to bond with the p orbitals of oxygen, and it's going to look like this, okay? So these p orbitals are on oxygen. They bond end to end. So it looks like that. Ooh, that one's ugly. So yeah, so those are all oxygens. Okay, so the oxygen, it's just the p orbital. It's not hybridized. Now, if it's hydrogen, then it would just be that one s orbital. Okay. Yeah, so they're not going to ask about hybridization of anything other than the central, because the central is the only one that hybridizes. So yeah, if you're struggling with hybridization right now, just memorize like the number of things attached to the central atom. That's, you know, what the hybridization is. But I will say, I don't know if you guys are like this, but for me, when I learn something the first time in a class and it's not really applied all that much, it makes absolutely zero sense. But then when I go to a higher class and that stuff is applied, then all of a sudden it makes perfect sense. So like when we did OChem, we went over this stuff again and as it relates to OChem, and just seeing that it is applied and it matters in real life, it made it much more intuitive, and so it made sense. So what I'll say is if you're not taking OChem, you don't even need to worry because you'll never see it again. If you are taking OChem, chances are it's going to make a lot more sense when you take that, okay? They don't usually ask a lot of super conceptual problems about hybridization on Gen Chem exams, okay? All right. Someone mentioned flux from a capacitor. Please never mention that ever again. That gives me PTSD. Oh God, that was disgusting. I definitely cried over capacitors. All right, so Number 9 says, according to valence bond theory, the triple bond in ethylene or acetylene, C2H2, consists of blank, okay? So basically, C2H2 is going to look like this. Okay, so you have 2 single bonds, 1 triple bond. So we're only talking about that triple bond right here. And so in that triple bond, we get 1 sigma. So 1 sigma bond, and we get 1 pi bond. Okay. So the answer is going to be, sorry, I miswrote. It's 2 pi bonds. Ugh. All right. So the answer is A. So there's 2 pi bonds. I hope I didn't give anyone a mini heart attack. I probably did, but that's okay. All right. So does anyone have any problems with 9? Okay. So what's your question for 9? The structure. Okay. That's a good question. So, all right. Ignore 10 for now. So someone said the structure of sigma pi bonds. Okay, I'm going to try and do this to where it's legible. So let's go ahead and just do the same molecule. So I'm going to not draw the bond lines. So I'm just going to draw these. Okay, so we know that each of these carbons here, those are going to be sp hybridized. Okay, so let's start with that. So they're going to be sp hybridized. So they're going to form sp hybridized orbitals like so. And so what's going to happen is the 1s orbitals of hydrogen are going to bond to those sp hybridized orbitals on carbon. But those 2 carbon atoms are going to bond with their respective sp hybridized orbitals. Okay, so what happens here, that bond right there, that is a sigma bond, okay? So that's a single bond, it's an overlap between orbitals, so that's a sigma bond, just like that's a sigma bond right there, that overlap, and that overlap is also a sigma bond, okay? So those are sigma bonds. Now what happens here, when carbon only has sp2 or sp hybridization, it's going to have some vacant p orbitals, okay? So this is where it gets a little bit crazy. So what's going to happen is, I'll draw these in different colors. So each carbon has 2 vacant p orbitals. Okay, remember p orbitals are dumbbell shaped. So I'll draw one that's sort of perpendicular to this plane, and then another that is parallel to the plane. So imagine the orange ones as sticking up and down, and imagine the red ones as sticking into and out of the paper. Okay, so what happens is 1 pi bond is 1 overlap of a set of p orbitals. So these orange p orbitals overlapping on both sides. So notice how they overlap on the top and the bottom. That orange overlap represents 1 pi bond, okay? Then if we have another set of p orbitals overlapping, then we have another pi bond. So there's 2 pi bonds in this molecule here, okay? They're not going to test over this. It's just someone asked in the chat box, so I just wanted to explain it really quick. Okay. No, we need to do 10 because they could give you a question over 10. Let's do 10. It's not as bad as it looks. So try 10. I'll give you guys 5 minutes to do that, and we'll go through the answer. because 10, like you would think it's heat, so it's back in like chapter 6 or whatever that was, but they just decided to have heat rear its ugly head in one of the later chapters with these heating curves. So someone said this isn't a coffee cup calorimetry question, is it? Slightly. Like some steps of it have to do with Q equals MC delta T, but some steps don't. All right, go ahead and spam your answer to 10. Good. Yep, so the answer is B. All right, so let's figure out why the answer is B. So some of you guys may not have really figured out how we actually solve these, and that's okay. So what this question is saying is liquid ammonia, which has a boiling point of negative 33 degrees Celsius, can be used as a refrigerant and heat transfer fluid. How much energy is needed to heat 25 grams of ammonia from negative 65 degrees Celsius to negative 12 degrees Celsius? Okay, and it gives us this information here. Okay, so there's going to be some steps that we need to solve. So first we're going to start out, and our ammonia is at negative 65 degrees Celsius, and it's as a liquid. Okay. And so what we need to do is first we need to increase it to the temperature of its boiling point, right? Because it's going to end up being a gas. So its boiling point is negative 33.4 degrees Celsius. And that is going to be as a liquid still, okay? So what happens then after we've heated it to this temperature, then we need to vaporize it, okay? So we need to put in the energy, we need to vaporize it. So that's as a liquid. So then we're going to change it from 33.4 degrees Celsius liquid to as a gas. So the temperature isn't increasing, it's just we're putting in energy to move it from a liquid to a gas. And then we need to increase it finally to negative 12 degrees Celsius. So negative 12 degrees Celsius, and that's going to be as a gas, okay? So there's a few steps here. So this first step here, we can use Q equals MC delta T, okay? So Q equals MC delta T, because all that's happening is a temperature increase, and we have the mass, we have the specific heat, it's given to us in this box here. We have the delta T because we're increasing from negative 65 to negative 33. So that's good. Next up, this is the point that confuses people. So this is the second step. And what we have to do is we have to multiply the number of moles times the delta H of vaporization. Okay, so the vaporization is sort of like this stopping, this checkpoint, right? You can increase the temperature, but then once the temperature is at the boiling point, then you need to put in even more energy to cause it to actually vaporize, okay? We need to change states. So that's going to be that amount of heat. And then once it's changed states from a liquid to a gas, then we can do another Q equals MC delta T problem, because it's the same state, so we can just do Q equals MC delta T. Okay, so what you need to know is increasing a temperature when you're not doing a state change, that is perfectly fine to do Q equals MC delta T. But you have to stop at each state change, and when you need to do each state change, then you just need to add in the step of doing the number of moles times the H of vaporization, okay? If this were as a solid, then, and we wanted to move from a solid to a liquid, then you would have the delta H of melting, right? Moving from a solid to a liquid. Okay, so now it's just a matter of plugging things in. So first off, Q equals MC delta T. So our mass is given to us. It's as 25 grams. Our C, our specific heat, as a liquid. So they have different specific heats as a liquid and a gas. So as a liquid, that's going to be 4.7 joules. And our delta T, that's just final minus initial, so you end up getting 31.6. Okay, and so when you solve that out, you're going to get 3,713 joules. Okay, so it's important to know there's a difference between this heat capacity as a liquid and as a gas, because if you think about heat capacity, that's the capacity of something to change by 1 degree Celsius with a certain amount of energy put in, right? So if you think about like liquid water versus water vapor, it's probably going to take a lot more energy to increase a gram of liquid water than it is a gram of gas, okay? A gram of water vapor, okay? So right now we're doing Q equals MC delta T to solve for the heat transfer in that first step. So we got that. Next up, we need to do the second step where we vaporize it, okay? So we do the number of moles. So we need to end up solving for that. So we get 25 grams, and in 1 mole, that's given to us right here. We have the molar mass is 17. So 17 grams. And so you end up getting 1.47 moles. Okay, so that goes in right here, 1.47 moles times that heat of vaporization, which is given to us right here. So that's 23.5 kilojoules per mole. And so that gives us an answer of 34.54 kilojoules. Okay, and so now we've vaporized it. So now this is a gas. Now we need to increase that temperature a bit more. So we can use Q equals MC delta T again. So Q is equal to, our mass hasn't changed. It's still 25 grams, but our specific heat capacity, now we need to take the one as a gas. So that's 2.2. And our delta T is just final minus initial. So it is 21.4. Okay, so putting that in the calculator, you get 1,177 joules. Okay, so just want to point out, these are given in joules because the Q equation gives you your answer in joules, but this heat of vaporization part right here, that gave us that heat of vaporization in kilojoules. So our answer is in kilojoules. So that's very important. So you just want to convert these joules from the Q to kilojoules to get an accurate answer, because these are all in kilojoules. So what you'll do is you'll convert each one. So this ends up being 3.7 kilojoules about. This is about 1.1 kilojoules. So you do 3.7 plus 34.54 plus 1.1, and you'll end up getting about 39 kilojoules. So that is our answer. Okay. Okay, so the number of moles was right here. So it gave us the mass, right? We have 25 grams and it gave us the molar mass right here. Even if it didn't, you could just calculate the molar mass of NH3. So I just converted from grams to moles right there. Okay, so this one right here, this 23.5 someone asked me about, that's the delta H of vaporization. So that's given to us right here. So the blue represents the equation I'm using, and the green just represents my work underneath. So H of vaporization. Okay. Oh, definitely not more than one of these on the exam, because this takes a while. This is a long problem. So someone's saying, why don't we convert to moles for the first part but not the second? It's because we're using different equations, okay? So with Q equals MC delta T, that's talking about mass. So we just use grams. But when we're doing our vaporization, it's the number of moles times the delta H of vaporization. So it's just something you have to know. Yes. Okay. So basically, the way you want to think of this, sometimes you might find like a heating graph, for example, where this is temperature. So the y-axis is temperature and the x-axis is energy. Okay, so you start off, your lowest form of matter is going to be your solid, right? So as you start off as a solid, and when you put in more energy, you get to increase the temperature, but all of a sudden you get to its melting point. So once you get to its melting point, then you have to melt it. And so when you're melting it, the temperature doesn't increase, but you are putting in energy, okay? So that's why we're not using Q equals MC delta T. We're using a different equation. And then once we've fully melted it, then we can start to increase the temperature a bit as we put in more energy. But then we get to its boiling point, so we need to put in some energy to vaporize it. Okay, so the temperature isn't changing when we're vaporizing it, but we are putting in energy. And then once it's fully vaporized, then as we put in more energy, the temperature increases. Okay, so I'll say this is a solid right here. And we use Q equals MC delta T. This right here, we're melting. So you use moles times the delta H of melting. And then this right here, we have a liquid. And so we can use Q equals MC delta T. And then right here, we are vaporizing. So we use the number of moles times the delta H of vaporization. And then at this point, we are at a gas. So we can use Q equals MC delta T. And so this is the route that you're going to take when you do these state change problems, okay? So maybe you start off somewhere, maybe along here as a liquid. So to get from this point to maybe this point right here, then you'll do Q equals MC delta T to increase to the boiling point. Then you'll do mole times H of vaporization to vaporize it. And then after it's vaporized, to get to that final temperature, you do Q equals MC delta T. Some problems may be just really long and they'll make you start off as a solid and end as a gas. So you have to do that full route, okay? Yeah, so you put the steps in each tier, perfect. So if you go the opposite way, then just think about putting in energy versus taking energy out. So if you're vaporizing something, you're moving it from a higher temperature, from a lower temperature to a higher temperature, then you put in energy. But if that's falling back down, what do you think happens? It just gives off energy, okay? So if we're going from this point as a gas all the way down, then what's happening is whatever substance this is just losing energy. So it's the exact same math. It's just your final answer will have a negative sign. So that's basically heating curves. Yeah. All right. So let's see. I'm going to have you guys attempt 14, and then I'll go through the answers for everything else after you've attempted 14. So go ahead and take 2 minutes to do that one. I'll keep this up. If you ever need like pictures of one of the previous pages, you can always ask me at the end of the session. Okay, so let's go ahead and go through 14. So I'm going to explain 14, and then I'm also going to answer the last few problems because this is the last session, so I can't go through, I have to do everything this time. I can't just procrastinate it off to the next session. All right, so number 14 says, what is the bond order of F2 plus? So use the molecular orbital diagram below to aid you. So first, what we want to do is we want to fill this thing in. So when it's asking about bond order, the first step, fill in the diagram. Okay, so F2, that has, fluorine has 7 valence electrons, and there's 2 of them, so that gives us 14 valence electrons, but this is a +1 charge, so we lose an electron. So we get 13 total valence electrons. So what we do is we fill this in, working from bottom to top. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we filled them all in. So now to find the bond order, so BO bond order, that formula is 1/2 times the number of electrons in your bonding orbital minus the number of electrons in your anti-bonding orbital. Okay, so we filled them all in, so now let's fill in this formula. So that's equal to 1/2. So the number of electrons in our bonding orbitals. So this is a bit hard to read, but just know that anytime there's an asterisk there, so there's an asterisk there, and there, that asterisk represents an anti-bonding orbital, okay? So the asterisk is anti-bonding. If there's not an asterisk, then it's a bonding orbital. So first, count up the number of electrons in the bonding orbital. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 of them. So 8 minus the number of electrons in our anti-bonding orbital. So 1, 2, 3, 4, 5. Okay, so 5 electrons in our anti-bonding orbital. So that's 1/2 times 3. So that comes out to 1.5. So the answer is A. So that's how you do your bonding orders. Yes, this would be paramagnetic. The bonding. Just to count them up. Yeah, so counting up the bonding, we get 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the bonding orbitals don't have an asterisk. The anti-bonding orbitals do have the asterisk, and I just circled those in purple. Yeah, so there's 3 places where it's anti-bonding. Okay, so now let me go. Okay, yeah, you don't count them if it's not filled in. You're only counting the number of electrons that are inside of either a bonding or an anti-bonding. And again, they'll always give you the diagram on the exam. Okay, so let me go ahead and go through these other problems now. So I believe we skipped 11. So 11 says, what types of forces exist between molecules of CO2? Okay, so I'll do this one in, what's the color I've used? Orange. So we'll draw CO2 down here. I've drawn it 1,000,000 times already, so this is my structure for CO2. Okay. So it's saying what types of forces exist between molecules of CO2. So it's only talking about 3 types. So London dispersion forces, dipole-dipole, and hydrogen bonding. Okay. So for any molecule, what's going to happen is this is sort of like a priority list or a tier list. So if it has something that's higher priority, it also has the bottom. So if it has hydrogen bonding, then it also has dipole-dipole, and it also has London dispersion forces. Okay. So what happens is we just go through this list. So first, we'll start with London dispersion forces and see if it has that. Now, pretty much anything is going to have London dispersion forces, so we know it has that. As far as dipole-dipole, we have to have polar molecules, and in this case, this molecule of CO2 is nonpolar, right? Because our vectors look like this. They cancel out, so the molecule is nonpolar. So we don't have dipole-dipole, and we also don't have hydrogen bonding, okay? So we only have London dispersion forces, so the answer is going to be B. So dispersion forces only. Yeah, so someone says dipole-induced or ion dipole. Probably not. That's pretty low yield. They could. I just didn't see it on the practice finals that I used to make this session. But just to review, so we also have, so I'll do 4. So we have ion dipole. That's self-explanatory. It's just an ion that is attracted to a polar molecule, okay? 5 is going to be ion-induced dipole. And what happens there is you have a very charged ion that gets moved close to a nonpolar molecule, and that charge on that ion causes the electrons in that nonpolar molecule to polarize, and so ion-induced dipole. So that ion induces a dipole in that molecule. Again, this is really low yield. And then 6 is dipole-induced dipole. And so that's the same logic between 5, except it's just a polar molecule inducing a dipole on a nonpolar molecule, okay? So, water, so think about like an ionic compound dissolving in water. Those ions attracted to those water molecules, that's an example of ion dipole. So dipole-dipole, the water itself would be an example. That's true. Just water molecules attracted to each other. Because if you think about a water molecule here, so I'll just draw this out. So the net vector on here is going to look like this. So we have partial positivity on the hydrogen side and partial negativity on the oxygen side. So what I mean by that, the oxygen side of the molecule has a negatively charged region, and the hydrogen side of the molecule has a positively charged region. So if I were to duplicate this molecule, what happens is, if you think about how opposite charges attract, then what happens if this oxygen molecule that I'm moving around comes to the labeled oxygen molecule? What's going to happen is that positive or that partially negative oxygen is going to be attracted to that partial positive region on hydrogen, okay? So those dipoles end up attracting, okay? So that's how dipole-dipole works. Okay. So yeah, that's IMFs. Again, these ones right over here are pretty low yield. I highly doubt they'll ask about those. Okay, so let's go ahead and move to 12. So 12 says, which of the following substances will have hydrogen bonds between molecules? Okay. So first off, we have CH3F. So that one looks like this. Okay, so those hydrogens are not attached to the phone, so no hydrogen bonding there. And B, hydrogen isn't attached to a phone, so no hydrogen bonding. With HCN, that one looks like this. So hydrogen is not attached to that nitrogen, so that's not an answer. H2S looks like this. And sulfur is not a phone, so D is not valid. So that leaves E as the only answer choice. And if you look at it, that looks like this. It's an ugly N. So NH3 looks like this. So those hydrogens are attached to a phone, so nitrogen is a phone. So hydrogen bonding can happen in NH3, okay? So that's 12. So then 13, which of the following should have the highest boiling point? So this one, highest boiling point, we're essentially asking which one has the strongest IMFs. Okay, so basically what's happening here, you have to look and see this pattern. A, B, C, and E, those are all going to look the exact same. It's a carbon and it's bonded to halogens on all sides. So I'm going to draw it like this. So X could refer to any halogen. Okay, so X could refer to fluorine, iodine, bromine, or chlorine. So what happens is you have vectors that are going to look like this because those halogens are electronegative. So they want to pull the electron density towards them. But what happens is those vectors end up all canceling out. So the whole molecule for A, B, C, and E is going to be nonpolar. So nonpolar and nonpolar. And then the same thing with CH4, that one looks like this. The only difference is that the vectors are pointing in this time because carbon is more electronegative than hydrogen. And those vectors end up canceling out also. So that one's nonpolar as well. Okay, so in terms of London dispersion, in terms of dipole-dipole, and in terms of hydrogen bonding. So dipole-dipole is out of the question. Hydrogen bonding is also out of the question. So the only form of intermolecular forces here is London dispersion forces. And remember, London dispersion force is based off the molar mass. So for all of these molecules, it's all a carbon central atom with 4 of the same molecules attached to it. So looking at this list, iodine is going to have the higher molar mass than fluorine or bromine, hydrogen, or chlorine. So that makes B is the correct answer. Okay, because Ci4 has the highest molar mass. Okay. So because Ci4 has the highest molar mass, it has the highest London dispersion forces. So it has the strongest intermolecular forces. So Ci has the strongest intermolecular forces. And so that causes it to have the highest boiling point, because when you have strong intermolecular forces, those molecules are all held together very tightly. So you have to put in a lot more energy by comparison to cause them to vaporize or to heat up or what have you. Okay. So are there problems with 13? So it was the highest London dispersion forces. So there's no dipole-dipole, right? Because these are all non-polar molecules. Dipole-dipole only happens when there's polar molecules. So, say someone asked, would it always depend on high molar mass? So say for each of these molecules, maybe some of these molecules did have dipole-dipole and some of them did have hydrogen bonding. So another thing that I want you to know, this was covered in the SI session we did over intermolecular forces, but just to clarify, hydrogen bonding is the strongest, so I'll rank these from strongest to weakest. Strongest to weakest. Okay, so H bonding is the strongest. So that's the strongest IMF. Then we have dipole-dipole, and then London dispersion forces are the weakest, okay? So what that means is, say these all had different types of IMFs, say one of these had hydrogen bonding and another had dipole-dipole and the rest were London dispersion. The answer would be the one with hydrogen bonding because that hydrogen bonding is stronger intermolecular forces than all the others, okay? By a long shot. So someone said, when it asks about boiling point, should we go straight to comparing masses? No, you only compare masses if they all have London dispersion forces. So the first thing you want to do is look at the type of intermolecular forces there are. If they're all London dispersion forces, then you look for the molar mass. But if there's a distribution, then you look for the one that has the strongest type of intermolecular force. Okay, so for NH3, that has hydrogen bonding because for hydrogen bonding, 1, you need to have hydrogen, and 2, it has to be attached to a phone. Attached to a phone. So that could be fluorine, oxygen, or nitrogen. And so in NH3, where was that drawing? That drawing is right here. So that hydrogen is attached to that nitrogen. So that means hydrogen bonding can happen. Okay? Only when hydrogen is attached to that phone does hydrogen bonding happen. And so if you were to look at this list of molecules right here and look at which one has the highest boiling point, then it would be NH3 because hydrogen bonding occurs in NH3 and it's the strongest intermolecular force. Perfect. Okay. So just let me make sure there were no questions I skipped. Okay. So we got 2 more. Okay. So this says, in which of the following compounds will the molecules not form hydrogen bonds with each other? Okay, so let's look at A. So this one is not going to have hydrogen bonds, actually. That made it easy. But let's go ahead and look at B. So with B, we have an OH right there, so that hydrogen is bonded to a phone. So just again, for reference, fluorine, oxygen, or nitrogen. So that hydrogen is attached to a phone, so this does have hydrogen bonding. Okay, so next up in part C, this hydrogen is attached to a phone, so that's nitrogen, so the hydrogen is there, so we have hydrogen bonding. Next up in D, that hydrogen is attached to the oxygen, so that's a phone, so we have H bonding. And lastly, again, it's attached to a phone, so we have H bonding. Okay, so in A, none of these hydrogens are attached to a phone, so there's no hydrogen bonding. That's what the question is asking for, so that's why A is the correct answer. Okay, so are there any problems with 15? Okay, so last one, so 16 says neon atoms are attracted to each other by, so these are just neon atoms floating around. Remember, intermolecular forces are not bonds, they're just attractions, okay? So there's no dipole because they're just individual atoms, so they can't have a dipole. So 3, London dispersion, dipole, and hydrogen. So there's no dipole. Also, hydrogen isn't even in the picture here, so there's no hydrogen bonding. So the only form of attraction we have here is dispersion forces. In terms of D and E, these are distractors, right? Because these are talking about bonds, but intermolecular forces are not bonds, they're just attractions. So D and E would not be answers. Okay. So that's the end of this session. So does anyone need any pictures or anything of these pages?
Yes, please.
Okay, sure. So I'll just go through each page for a couple seconds and then I'll scroll through. That's sad. This is the last session. I hope I can. It's a matter of me getting an A in the class and a matter of like the spot being open. Yeah, so okay, so 6 should be on this page, yeah. So to the person taking pictures, I'm just going to spend a few minutes on 6 so I can explain. So 6 says, which of the following pure substances has the strongest dispersion forces? With dispersion, we know that the only factor to consider is the molar mass. So the higher molar mass has the highest dispersion forces. So among all of these molecules here, B has the highest molar mass, so it has the highest dispersion forces, okay? And then you wanted 7 also. So 7 says, what is the hybridization of the central atom in HCN? This is my Lewis structure for HCN right here, and I drew the structure out. Carbon is our central atom. Remember, only the central atom gets hybridized. So with hybridization, it's just a matter of how many things are attached to that central atom. There's 2 things attached to the central atom. So because there's 2 things attached to the central atom, it's sp hybridized. Okay, so let me go ahead and move on to this page for the person taking pictures. Yeah, good luck to everyone on their final, by the way. I think you guys are going to do well. Okay, so a couple more seconds on this page and then I'll move to the next. All right. And then this was the last page. Okay, so was there any more questions or anything before I go ahead and end the call? You guys are all very welcome. The last one, did you want an explanation? Oh, sorry, I did miss one there. Yeah, so 16 is C. I really just try and go to the online ones just because I have the option and I'm lazy, so yeah. But she only has one more tomorrow, so I'll just be there on Blackboard. Thank you guys so much. Oh my gosh, that makes me happy. I'm glad I was helpful this semester. The math ones are probably going to be typed. You'll probably type in the answers for math. Oh my gosh. Yeah, I'm going to miss you guys. I'm sad I'm not doing 1308. I'm just not smart enough to do 1308. I would continue along. I'm pretty sure they're good for 1308. Like, I'm pretty sure like 200. I remember last semester, one of the 1308 people had like 200 people at his test prep session. So that probably means he's good. So yeah, no, I'm not doing 1308. Yeah. Because most of us, we just do a subject and we stick to it unless we jump around. And I would jump to 1308. It's just like, to be an SI leader for a class, you have to know it. Like, you have to be able to do it practically in your head with your eyes closed, with your hands behind your back. So 1308, that's me. But 1307, that's me. 1308, I made the A in and everything, and I did well. It's just, I wouldn't be able to explain it as well as 1307. So that does you a bit of a disservice, and it's just not fun for me to like do something that I'm not super good at. So 1307 for now, but I may do OChem 1. So if I get an A in OChem 1, you may see me again next year if you take that. I know it is. You guys have definitely been my best set, because I did 1307 in the summer semester, but like only 5 people came to those sessions because like the class size was tiny. So yeah. Yeah, some people are really glad to be done with chem. I'm taking all the fun chem and then I'm getting out after that. I'm done after biochem. I'm not taking P chem or A chem or any of that stuff. I think you'll pass. I think you guys are going to do good. I think you guys have a couple days at least before the final. So that's plenty of time to go ahead and go through what your week in and, get comfortable with it. Yeah. And I'll still be in the group me, so like you guys can ask me some last minute questions. Yeah, it should be 50. Yeah. So it'll be 50 questions and you'll have more time because it's 50 questions. So, yeah. Okay, so I'm going to go ahead and end the call now. So, yeah. So good luck on your finals. It was great having you guys this semester, and I hope you guys end up doing well on your future classes and all of that. So, yeah. All right. Goodbye. Thank you for coming to my sessions this semester.